Physics 11 is generally now that we're actually getting into the physics, is generally a fairly frustrating course for some students. I shouldn't say generally, but can be a frustrating course for some students. Lots of the topics we're going to talk about you're going to be familiar with already to some degree. The problem with your understanding is that unless you've actually done some formal physics education, you don't necessarily have the framework, the formalized mathematical framework for a lot of the stuff that we're going to talk about. And so you may feel like you've got a particular understanding. The vocabulary you might be familiar with, you're going to want to use interchangeably, but I'm going to start to add definitions to words that you're already familiar with that are perhaps going to force you guys to unlearn some of the stuff that you've already become familiar with over the course of your 16 or 17 years on this planet and force you to reframe a bunch of it. And so much of this course is you guys just having to reframe and redefine stuff you feel like you're already familiar with. And the quicker you can do that you can accept the changes that I want to make to your existing framework, the better this will be for you. The more resistant you are to that process, the worse this is going to go for you. So much of physics education is just undoing what you think you know already. So here we go with kinematics. Kinematics is the study of motion. And you guys have been moving since you were born. And you might feel like you're fairly comfortable with it all already. And we're going to put a mathematical framework to the stuff that you're already familiar with. So kinematics is the study of motion. And I'm going to add in here, it's the study of what I would call normal motion. This word normal, we're going to give it multiple definitions over the course of this semester, but as far as what I mean here, it's your standard everyday, you're walking to school, you're riding a bike, you're driving a car, normal motion. Things get weird as soon as you start moving in circles, so we're going to ignore circles. Things get weird when you start moving very, very quickly. So we're going to ignore very, very quickly. When I say very, very quickly, I mean like percentages of the speed of light. We're going to ignore that because weird things happen when you move that fast. We can't use normal kinematics for that. So straight lines, standard speeds, this is the stuff that we talk about in what I would call normal motion or kinematics. It's the how of so much of what you guys do already, the how fast, the how far, the how long. Relatively simple concepts. And language is going to be really important to us in this unit. So all quantities in physics fall into one of two categories. They are either called scalar quantities or we call them vector quantities. Hands up if you've heard of either of these two words before. Reina, which one and in what context? In what class? Math 10? Yeah. Your teacher's talking about vectors in Math 10.
He used to mention them a lot.
Okay.
He's like, you'll learn about it.
You'll learn, which is right now. Later is now. Any of the rest of you, scalars and vectors? Hands up if you've seen the movie Despicable Me. The first one. So then when I'm asking about scalars and vectors, all of your hands should have gone up. Where do one of this shows up in Despicable Me, the first? Where? Do you remember?
Direction and magnitude.
Yes. So there is that scrawny little dude with a bit of a paunch when he's applying for a villain loan at the villain bank. Gru goes there and he's sitting on the long couch. And the weird dude with the big glasses comes up and sits next to him. And actually happens to be the son of the banker, if I remember correctly. And has his piranha gun. And he says that his criminal name is Vector. And he goes on to explain that it's Vector, and he throws up one of these because I commit crimes with both direction and magnitude. And then he thrusts awkwardly, as you can, at the camera in an animated movie. And then So those of you who've seen the movie, perhaps remember the scene. So a vector quantity is exactly what was described there. I don't know why they went there with that particular character, but any vector quantity is a quantity. Quantity with both direction and magnitude. And so we classify these things because it's easier to say, oh, it's just a vector quantity. This is a vector, this is a scalar, this is a vector, this is a scalar. And then to qualify them as we go, with the understanding that a vector quantity has both direction and magnitude, and so we have to figure that out, and we have to use them, both the directions and the magnitudes, when we're talking about these things. Direction is fairly straightforward. You're familiar with directions. Directions are things like, well, actually I'm going to put one of these down here. And one of these over here. Perhaps you're familiar with this. Let's fill it full of directions. What are all of the directions? Start saying things. North, yes, we like north. We like east, south, west. Cool. What other directions are there? Up. We like up. Up and down. Side to side is too ambiguous. Left and right. We like left and right. That's basically all of them. Yeah. Ooh, forward and backwards counts. We're not going to work in 3 dimensions yet. That'll come later, not this course. So we'll say forward and back are like this. We'll just assume that forward is to the right, back is to the left. Doesn't have to be. You can swap those. But generally speaking, we would call forward to the right and backwards to the left when we're drawing a diagram of something happening. And we need, in addition to the words here, we need to be able to talk about these things in math terms as well. So as a general rule, some of these directions we say are, generally speaking, mathematically positive. Some of them are mathematically negative, generally. But these things are allowed to switch at kind of arbitrarily. Generally, as a general rule, and then because I've drawn these on an XY grid, you've got an understanding of which directions are positive. Inherently speaking, if I draw this, which directions do you assume to be positive? Up and right are generally positive. So this is positive generally, this is positive generally, which means the opposites of those are generally speaking mathematically negative. So that's going to be negative, that's going to be negative. But positives and negatives are just defined to be that way. It's totally arbitrary. Someone said, well, we need some direction to be positive and we need some direction to be negative. So let's just say these two are positive, these two are negative, and work with it. But as far as the stuff that we do in math, or in physics rather, sometimes it's going to make sense to swap those. Sometimes it will make sense to call down positive and up negative. And as long as you're consistent, once you've defined it a particular way, you will be fine. But as a general rule, we call them left, back, west, south, down, all negative, north, up, east, right, and forward are generally speaking positive. The reason for that is because the universe is right-handed. For those of you who are left-handed, I apologize, but the universe is conspiring against you. Yes?
It's different in some countries, right? Isn't manga written
So the way you read, you mean left to right? Yeah. So yeah, some countries read right to left, but the mathematics of the universe are still such everywhere. I mean, universally, the universe is right-handed. And as you advance further in math, you'll see what I mean. But at this stage, just take my word for it. The universe is right-handed. So that's direction. It's exactly what you expect it to be. Magnitude is what? What does that word mean? Where are you familiar, or where have you heard this word magnitude before? Speed? What do you mean? Okay, in that context, what does it mean? Yeah,
Means like amount.
an amount of something. Yeah, that's all that a magnitude is. A magnitude is the size of something. So generally speaking, the most common place that word magnitude gets thrown around is when we're talking about earthquakes. What was the magnitude on the Richter scale or on the decibel scale? How loud is the volume? Magnitude is just the size, just how big something is. So if a vector quantity is a quantity with both a direction and a magnitude, then a scalar quantity obviously is going to be different. Which of these two can we drop off and still have a meaningful discussion about a topic? Is magnitude more important or is direction more important when you're talking about a concept? What are we talking about though if we're just talking about something being west? Magnitude. The magnitude is the more, is the one that we have to keep if we're going to still talk about a topic. So like volume is the example that I used before. Like how loud something is. The volume of music has not, like there's no direction there. It's not like the volume is going that way. It just is. And so there's lots of topics that just are, and we want to talk about how big they are. So a scalar quantity is a quantity with only a magnitude. And there's lots of these particular kinds of quantities that it doesn't make sense to talk about a direction. Lots of examples, things like volume, and not like volume as in how much something is holding, though that could work as well. But like volume for like sound. We don't care which way the sound is going. The sound just goes. What's another one? We don't, a something that you could measure where the direction, where it would not make sense to include a direction. What are measurable things? Yeah. Time. Time's a great one. There is no direction to time at this stage. That will change later if you continue to study physics. But generally speaking, time only goes forward. You said height? That word implies a direction. When you're talking about height, what are you assuming? Up. Upness is assumed there. So we're talking, we can throw that into a vector quantity. That word, there's an implied direction in that word. Yeah, Brad.
Speed.
Speed's going to be one of them. Which one? A scalar? You're right. Speed is a scalar. For those of you who have your driver's license, hands up, just of curiosity. How many of you have your driver's license? Anyone. Just you can drive a car legally. I'm not going to encourage you to drive a car illegally. For those of you who can legally drive, you have a speedometer in your car. It does not matter which direction the car is going. That speedometer always counts up. If you don't believe me, next time you're driving, find some big open empty road and go backwards as fast as you are comfortable. The speedometer doesn't go down. The speedometer will only ever go up. Whether you're going forward, 50 kilometers per hour, or backward, 50 kilometers per hour, the speedometer only ever counts positively. So that is speed. Speed's a scalar. But speed has a brother where direction now all of a sudden matters. What's another word that you sometimes replace speed with? No, it means similar things to distance. Ooh, we'll come back to distance. Velocity. This is one of those concepts. Lots of people say, okay, speed, velocity, same idea. Not true. Speed, you have a speedometer in your car. Speed doesn't care about direction. Speed will only ever count up regardless of which way you go. Velocity, though, velocity is a vector. If you take your speed and you combine it with the direction you're traveling in, now you've got a velocity. Velocity cares about which way you're going, speed does not. So if you didn't have a speedometer in your car, if you had a velocimeter in your car, when you went backwards, that needle would actually go down. But it doesn't. So you have a speedometer, not a velocimeter. Yep. Brad, you had your hand up.
Is velocity about like how long something can go in whatever direction, like in the same place? So if you like shoot a bullet, is it like how long the bullet can go? It's like down a straight path before it starts like losing its velocity and starts going down.
That's taking it a step too far. Speed and velocity, conceptually, speed and velocity are almost the same thing. Anywhere you would talk about speed, you can also talk about velocity. The only difference between the two is velocity cares about which direction you're traveling. So if you're talking about, I went 50 kilometers per hour, that's speed. I went 50 kilometers per hour forward, that's a velocity. That's the only difference, is you tack on a direction to the speed that you have. And so often, speed will be referred to as the magnitude of velocity, because that's all speed is. Speed is the how bigness. Velocity also cares, though, about the which wayness of it all. What are some other concepts that we measure, some of us far too often, that wouldn't have a direction? Oh, Ray Reed, you talked about distance. You were correct. Distance is a scalar. Distance does not care which way. Distances are just distances, how far you've gone. If I walk back and forth across the glass, I will demonstrate. Why the heck not? I'm sitting for far too long. I walk to the door. How far have I gone? Ballpark. 30 feet. Okay, cool. I walk back. Distance doesn't care how far, or sorry, the distance doesn't care which way. Maybe I've gone 60 feet, if that's the units you want to use for my distance that I've traveled. But have I actually gone anywhere? I traveled 60 feet, but did I go anywhere? Is it a different thing? Okay, then one second. Hold that thought, Brad. So I haven't gone anywhere. So distance does care. Distance cares about just about how far I've traveled. So I walked 60 feet. There is a concept similar, so the same way that speed and velocity are related, there is a concept that is related to distance that cares about the direction I travel. It starts with the same set of letters even. What's the word that you might be familiar with? What is it? There's a word, it means to have moved something. Never mind. What were we going to say? I think I just heard it. Colin? To displace something, yes. So the concept that is a vector is displacement, which is actually down here, and we're going to talk about it in more detail in a second. But the idea of displacement is I walked, my distance I traveled, but was I displaced at all at the end of it all? I ended up where I started. I was not displaced. Even though I traveled the distance, my displacement would be 0. Because displacement cares about the direction I traveled. And if you travel opposite directions, they're going to cancel each other out. What are some other values we measure that either do or don't have direction?
Is weight a scalar quantity?
You said is weight?
Yeah, like step one. Or, right, isn't it? Because like it's like points.
That's a great question. What is weight? We're going to talk about that in a couple chapters too. What is your understanding of weight right now? If I asked you what you weighed, what would you answer? Too much. Okay, don't give me the number, give me the units. If I asked you for your weight, you would give me a number in pounds? How many of you would give me number with a different set of units? My Europeans would, for sure. Dana? You give it to in kgs, okay? And this is where what I said right at the beginning, where we're undoing a lot of what you think you understand already. Weight actually has a direction. Weight is a vector, but there's a concept related to weight, and weight is measured in pounds. So if I asked you for your weight and you gave it to me in pounds, you'd be correct. If I asked you for your weight and you gave it to me in kilograms, you'd be wrong. Giving it to me in kilograms is not weight. It's a concept related to weight, starts with an M. Your mass. Mass is a scalar, weight is a vector. And here, and we'll talk about it when we talk about dynamics, but I'll mention it briefly here. The easiest way to think about it is to think about what happens when it's gone. Can you be weightless? You can float. Where do we often talk about weightlessness? In space. So in space, you talk about being weightless all the time. Well, astronauts would. They look, if you have seen footage from the International Space Station, they're just kind of floating there. We'll talk about what they're actually doing because they're not floating; they're actually perpetually falling, which we'll talk about in a couple chapters. But are they ever massless? No. At no point are you massless, but I can make you weightless. Is toss you out the window for about 10 seconds, maybe about 5 seconds. You'll be weightless. It's actually longer than you think. You can be weightless, but you're not going to be massless. And so there's a relationship between these two. One has a direction, one does not. Yes, Emma. What about density? Density, that's a great question. Density is a scalar. Density has no direction. We don't care which way the density goes, it just is. It is a property of elements, and every element has its own density, does not have a direction associated with it. I think we've got a pretty extensive list. There are more. The only other thing I'm going to add here is that just as far as what scalars and vectors are, these are just mathematical objects. And as such, they're going to behave mathematically. It's abstract, it's going to be weird, and that's okay. But these are just mathematical objects. So let's talk about some of these specific ones. One you did not mention is this idea of position. Position is the most fundamental thing we talk about, the place to start in kinematics, because what is position? What is your understanding of that word? What does that word position mean? Where you are. So Brad, where are you? Sitting on my chair. That's a bold word. I don't have a seating plan. Where is your chair, Brad?
Ahead of and to the right of the doorway.
So when you mean ahead, because ahead for me is towards DeVries's class. Can you be more specific? If it would help, that direction's north.
Oh, okay. So, northeast
of the door. Okay, so the of the door is really quite important here. Because if you just said northeast, you could be anybody. From Jack to Sire to Alana to you, right? You have a distance in your head, perhaps you didn't say it, but there's going to be a distance associated with it. You had a direction northeast of the door. So position isn't just saying where you are isn't enough. It's where you are relative to some landmark. If you're at a concert or you're in a city, you're visiting something you're not familiar with perhaps, you're going to visit someone, you're at an event, anywhere, any large open space, and someone is looking for you. When you tell them where you are, it's always going to be relative to some other location. I'm at such and such a gate at the Abbotsford Entertainment Center, or I'm at such and such a gate at Rogers Arena, or I'm at this entrance to Stanley Park, or I'm this far from the 7-Eleven. Like everywhere, when you talk about where you are, you're always going to give it some sort of landmark, And when I say landmark, what this means is, when we talk about it conceptually, a landmark is some agreed upon origin. If I break my leg and I cannot walk, and I ask you to come pick me up, and I tell you I'm at the 7-Eleven, is that enough information to come find me?
No, because
There's multiple 7-Elevens. I'd have to tell you which one I'm at. I'm at the Immel 7-Eleven. That's enough information. We agree, as a society in Abbotsford, you know where the Immel 7-Eleven is. Because I've given you the street name and I've given you the convenience store. Okay? So we've got some agreed upon origin. Sometimes it's implied, just by the fact that we all live in the same city. We all agree that this street name has this name. None of you are going around arguing about street names. IB Senior's not on Bevan, it's on South Fraser Way. No one's arguing about that. And so we've got some agreed upon origin. In math, that word origin means what? What numerical value do we give to the origin? 0. So when we take this concept and we turn it into math, you're going to give me a position relative to some value you're calling 0. So Brad, if we go back to your example, where are you?
northeast of the door.
Okay, hold on, let me get to the door. Okay, northeast. We can agree which way is, if you believe me, if that way is north, that way is east, northeast would be that way. Okay? You're northeast. How far? And are you northeast? That's north, that's east. Northeast is 45.
Yeah.
You're actually, if we're going to get really picky, and we're going to, physics is all about getting really picky with the words you choose to use. You're actually north by northeast. Believe it or not.
That's saying that I have a bigger, like,
you're more north than northeast.
Positional bias to the north?
It actually means, yeah, you're halfway between north and northeast.
Okay.
North by northeast is,
oh yeah, okay, I got it.
It's halfway up to 45.
Okay.
And now, how else, so I've gone north by northeast. I'm at Jack. You're not, it's not you. So what's your position? Where are you? Ballpark it. Estimate.
Okay, 25 feet.
25 feet. Let's see if he's right. Here's Brad. Oh, 28 and a half feet. It's pretty good. Only up by 4 feet. So in position, everything matters. All right? Yep. You've got a distance that matters. You've got a magnitude that matters. Direction and magnitude. And so that means that position needs to be, is what? It wasn't listed. Position is a vector or scalar. That's the word I'm looking for. Position is a vector, based on what I just tried to demonstrate. I couldn't just get to Brad when he said north by northeast. I had to go a particular magnitude as well. But he gave me both. We have a symbol for position. The symbol for position, I'll go this way and I'll give it to you. The symbol for position is the letter D with an arrow above it. The arrow above it, any concept that we talk about in physics that has the arrow means it's a vector. Some textbooks won't include the arrow. Some textbooks will just bold, excuse me, will just bold the letter. But I'm not going to do that because writing in boldface type is weird. So we're going to include the arrow. This is position. It's where you are relative to some agreed upon landmark. It's a vector, that's the symbol. Distance. Distance is, we talked about it already a little bit. What time does this class end? It's going to be quick, isn't it? 10:50? Okay, I'll just talk to them. We'll just talk about physicsy things till the bell goes. Distance. Distance is, it's a few ideas. How far away something is. We don't care about which way. We just care about how far away. Distance is the how far away something is. It's also how far you've traveled. So like I walked to the door and then I walked back. Lachlan figured it was about 60 feet. And based on our measurement from the door to Brad, 60 feet's a really good estimate.
That was the hypotenuse.
It's actually not a hypotenuse. It's the radius of a circle, believe it or not.
Radius is what?
Yeah.
But it's a triangle.
So no, it's not. Here's the problem with distance. Oh, Kai, I love it. You gave me a reason to walk around again. Here we go. So, problem with distance is this. If you tell me you're 28 feet away, where are you actually? Let's not go 28. 28 is really far. Let's go 12. 12 is a lot less far. Well, actually, 12's not far enough. Go 15. 15's back here. I lied. 18. I like 18 better. Okay, here's 18. And this is why it's not a hypotenuse. I am 18 feet away. From what? I don't know. Doesn't matter. But so is Raina. So is kind of Emma. Oh, yeah. Well, this is going to be really awkward for you and Jack. I apologize. I'll try and go up. Emma's also 18 feet. So is William. William's also 18 feet. Good. So is sort of Dwayne. I'm a little past Dwayne. So is almost the ladder. You see why this is a radius and not a hypotenuse? Because if all I'm concerned about is how far away something is, if I kept walking and just, I mean, the wall wasn't here, what path would I be tracing out? I'd be making a big circle. This is the radius, sorry, of a big circle. I've just swept out a quarter of it. So distance is the how far away something is, though it doesn't actually tell you where the object is, it tells you how far you'd have to go to get there. It's the how far you've traveled, and we're going to make a note here. When I say how far you've traveled, it's the actual ground covered. So when we're talking about distances, and let's say you're going to Science World. Distance is not, oh, I pulled out a map and it's the straight line from Abbotsford to Science World. Distance would actually be, well, I went a couple kilometers south to get to Marshall Road, and then I went a couple more kilometers west to get to the freeway, and then I went a couple more kilometers, and I kind of curved. Like it's actually the wheels turning, the walking happening, ground you've covered. Another important thing to reference here is that distances always add. You never subtract distances. And so this is actually going to make, because we don't care, distance doesn't care which way we're going, this is actually a scalar. And as if things didn't need to get confusing, distance is the letter D without the arrow. Conceptually distance, yeah, different. Yes, Rana.
And then it's like the ocean's going, right? Would that be like
What do you mean the ocean's going?
like the ocean's always moving, but at the same time kind
I don't understand the question.
The tide going in and out.
Is that what you're talking about? You're talking about tides? You're talking about currents? What about it?
It's just, I don't know, it's funny how like the ocean is still, like it's always in the same place, but it's also moving.
The last unit we're going to talk about is a unit on waves, and the ocean's going to come up there. It's complicated. These concepts, as far as what we're talking about at this stage, we're going to keep it a little bit more simple. If whatever you're measuring cares about which way you're going, it's a vector. If it doesn't care about which way and it just cares about the fact that you've gone, it's a scalar. So we've got position. Position is where you are relative to some landmark. Distance is how far away something is or how far you've traveled. And now we've got displacement. We talked about it a little bit already. Displacement is how far you've moved relative to where you were. And believe it or not, that's actually different than distance. Here we go. How far you moved from where you started. Oh, some time. I'm gonna walk around again. I'm gonna walk back to the door. Unless you have a really good reason to be on your phone, Henry, I want you to put it away. And I'm gonna go back to my computer. We've already established that that's about 60 feet, and I'm gonna go over here to the TVs. Now I'm gonna go back over here, push the desk back in. Distance cares about the path. Out, 30 feet, back, 30 feet, over. Maybe 20 feet, over, 15 feet. How far have I gone? What would distance say? 60, 20, 15, 95 feet, maybe? Because distance cares about the actual path I covered. Displacement, we'll go back to this and I'll come back to you in a second, Red. Displacement is how far I moved relative from where I started. So displacement doesn't care about the journey I just took. Where did I start this journey? I started at the chair. I started at the chair and then I walked out. I walked back. I walked over. That's where I started. This is where I ended. Displacement just says we started over there and ended over here. That is about how far. Sure. I think it's a little, that might be a little big, but let's say hypothetically that's right. Jack says it's 40 feet, it's 40 feet. But 40 feet, if I'm 40 feet from the chair, this is 40 feet from the chair. But this is also 40 feet from the chair. So if displacement cares about where I started and where I ended, then displacement also needs to have what other piece of it? Just hypothetically, it's more. Oh, you're debating. Displacement. So we've got a magnitude. Well, what else does displacement have to have? If it cares about where I am. Direction relative from where I start. So the direction relative to where I start, I'd be about 40 feet. Which way? That way is north. Yeah, east is that way. Southeast, sure. I've got a direction, and I've got about how far I've been moved. Doesn't care about the path I took to get here. All it cares about is, well, there he was, now he is, and this is how far he's gone. So, how far you moved from where you started? A few more pieces to put in here. Well, let's start here. It's the straight line distance. And direction. From start to finish. So that makes this thing a vector as well. And conceptually, displacement is actually related to something we've already talked about. If displacement says, well, he was here, the concept of here is which of those concepts? I pointed at this. No. The origin could be anywhere. That door could be the origin. My position. So I was here. I ended up over here. What is this? What is here? My new position. Okay. So displacement really is just the difference between two positions. And so that gives us a mathematical way to proceed with this idea of displacement. Here we go, another one. Displacement mathematically is a change in position. And so when we want to measure the change in something, what mathematical operation do we typically do? Let's say you're going to the gym. We go to the gym for two reasons. What are the two reasons we go to the gym? One of them is to get big, in a way, and another reason we go to the gym is to get smaller in a different way. You want to put on muscle, you want to lose fat, ideally, if you're going to the gym. So if you're going to measure progress at the gym, what are you doing mathematically to measure this progress? Measuring your weight, ideally when you start, and then again at the end. And doing what with those two values? Looking at the difference. So a change in position, and it's always where you have come to, where you've gotten to, minus where you started. If you're going to the gym, and if what you're looking at is your weight, you'll say, I started at this weight, I ended at this weight, I lost, I don't know, 20 pounds, whatever it is, whatever happened. Maybe you gained weight, maybe you put on a ton of muscle. But it's always this, when we're talking about a change in something, it's always a final value, or in this case, a final position, minus an initial position. And so this is actually going to give us, this idea here is going to give us, sorry, this idea right here, is going to give us the symbology for this idea of displacement. Because displacement is dependent on position, it's going to use the same kinds of symbols. Displacement is, it's going to have the arrow, sorry, it's going to have the letter D, it's going to have the arrow above it, but we care about a change in something. There is a letter that we use, it is not English. There is a symbol that we use to represent the change in something in math. What is it? Does anyone know? It's a symbol we use in math to represent the change in something. It is a triangle. So the symbol for displacement is a triangle. This triangle means change in. It is the Greek letter delta. And it is a change in position, which is exactly what we're doing mathematically here. So change in is always a final minus an initial, and then this is the concept. What's changing? Well, in this case, it's position. So do a couple examples down here at the bottom. Here is a person. I'm not an artist. They are a stick person. This person goes for a walk. They go out, they come back. They went out 6 meters, they came back 4 meters. What is the distance that has been traveled? Sorry? 10 meters. How'd you do it? Just add them together. 6 meters plus 4 meters equals 10 meters. Distances only ever add. They don't care which way. What's the displacement? Let's answer that question tomorrow. Have a great day. We'll see you later. Welcome to the nitty-gritty, very picky world of Physics 11.